Welcome back to Hardware Unboxed. Today's video is something I wasn't originally expecting to make, but yeah, should be rather interesting. So a couple of weeks ago now, I published a video on the Asus TUF Gaming A15. This very laptop here, stating a few reasons why I don't think it's a very good laptop and why ultimately I don't think that you should buy it. The reasons centered around two major issues with the laptop. One was the display, which has a poor color gamut and woeful response times. The 66% sRGB coverage makes it unsuitable for use with creative applications, which is particularly annoying for those that wanted to harness the power of AMD's Ryzen Mobile 4000 APUs for productivity. And with an average response time of around 19 milliseconds, the level of ghosting and smearing present with the display also makes it unsuitable for gaming. The other reason was around the cooling solution, which I described as terrible. Asus decided to block some of the exhaust vents and severely limited airflow to the CPU and GPU cooling fans by not having a direct air intake over these fans on the underside of the chassis. This led to very hot CPU temperatures, hot GPU temperatures, and a loud cooling solution overall. I showed that in taking the bottom panel off, allowing more air to reach the fans, CPU and GPU thermal performance improved, and that theoretically this would allow for either better performance on these parts with maybe a higher power limit or lower fan noise. Following this video, we had a number of requests to cut holes into the bottom of the chassis to see whether this would deliver the sort of cooling improvements that I was talking about. Asus also got in touch and were very angry about the initial video, claiming that their final cooling design for the A15 had the best overall thermal performance, that's a direct quote from Asus, and that their design is specifically engineered with certain things in mind. So we're going to be exploring both things in this video today. I'll be cutting some holes in a brand new Asus TUF Gaming A15 FA506IV that I bought at retail in the last couple of weeks with the goal of improving airflow to the cooler and thus getting better thermal performance. We'll also be talking through Asus's claims about their design to see whether there is any substance to be found there. Before getting to Asus's claims, let's walk through what I found when modifying the base of the A15 with the Dremel. Gotta say, first time I've ever modified a laptop in this way, but it's been a bit of fun to potentially destroy a laptop that cost over 2,000 Aussie dollars. We definitely wouldn't be able to make this sort of content without the support of our Patreon members. My primary issue with the stock design is there are no holes directly over the air intake ports for the cooling fans. This forces air through the chassis in an indirect path. Asus has reasons for this, but it is not optimal for actually getting air into the fans. Anytime the airflow path is altered on the way to the fan, such as by moving over components or changing direction inside the chassis, this reduces flow rate as energy is lost in the system in making these path alterations. So to achieve the same amount of airflow over the heat sinks, the fan has to work harder, or if it can't work harder, the ability to transfer heat out of the system is reduced. You will have seen this principle at hand anytime you try and obstruct direct airflow into a fan, you'll see that the airspeed reduces. If the goal is to get as much air as possible through the fan, and in this case into the heat sinks for heat transfer, you want as few obstructions as possible. My goal with these modifications was to add small vented grills directly above the blower fan intakes, adding in vents that Asus engineers decided weren't optimal for this design. I wasn't going to cut out the entire bottom panel or cut out large sections of plastic, but just add in some vents with a similar design to the vents Asus are already using. Of course, a disclaimer here, I'm not actually suggesting owners of the A15 go and make these cuts into the chassis. This is purely for science. Doing this obviously voids your warranty and I would not recommend doing it. I've sacrificed this laptop here as an experiment so that you guys don't have to. So after a bit of precision work with the Dremel, and I'm not an expert at using a rotary tool, so you'll have to forgive my less than stellar handiwork here, I was able to create some reasonable looking vents in the areas I wanted, in a similar style to the existing vents. These vents are also the bare minimum to actually get reasonable airflow into the fans. As you'll see, my cuts don't even encompass the entire fan area. There are still some areas to the fans that are visually obscured, as you can see here. I also haven't yet tackled the blocked side vent. That is a process that irreversibly alters the heatsink, so we'll leave that for later. Let's first explore the results of cutting holes into the bottom of the chassis and getting more airflow into those fans. The first thing to explore is how do these modifications improve the thermal performance of the system. For this, I first looked at a full IDA64 CPU and GPU stress test in 22 degrees Celsius ambient conditions from a fully cold start. So the system has been left off for at least 1 hour, it's then been turned on and run the stress test immediately. And after 30 minutes, the results are what you see here. In terms of CPU temperatures, I only saw about a 2 degrees Celsius reduction from 95C down to 93C. However, AMD's maximum allowed temperature for Ryzen 4000 APUs before throttling down the clock speed is 95C. So with the modified base running the CPU at 93 degrees, we're below the throttling point, and so the CPU runs at an average all-core frequency of 30 MHz. With the stock configuration running at 95 degrees Celsius, there was a small amount of throttling, dropping the CPU down to a 2800 MHz average, which is below the base clock. This means that with my modified design in a normal operating environment, the CPU is clocking 8% higher in this stress test. GPU temperatures also improved with the modified setup, dropping by 5 degrees Celsius, which led to a small but largely negligible improvement to GPU clock speeds, thanks to NVIDIA's GPU boost algorithm that tends to push clock speeds higher the lower the GPU temperature is. Next up, I put the laptop through a further IDA64 torture test from a hot start. So this time, no letting the system sit for an hour in an off state. This is starting the stress test again after about 1 minute of cool down from a previous stress test. I then let the stress test run for another 30 minutes. So in total, about an hour of stress test with a 1 minute break at the 30-minute point. So this is where the footage begins. Here we are looking at the system with the vent modifications running comfortably around 2.9 GHz long term. Then you'll see that I'm going to lift up the base of the laptop and apply tape over the vent holes that I cut out, effectively restoring the laptop to its stock vent configuration. Within 10 minutes, the average CPU clock speed has dropped to 2.3 GHz. So that's a pretty significant drop in clock speeds, and certainly more than I saw in the initial test. Upon removing the tape, CPU clock speeds are restored to around the same 2.9 GHz that we were seeing earlier. I repeated this test a second time using Asus's internal method of stress testing, which is by using Furmark and Prime 95 running together. This was to see whether I could confirm their internal testing, which I'll talk about soon. Here we have a clock speed chart over time after 1 hour of stress testing, running at 25 degrees Celsius ambient temperatures, which is also what Asus was testing with. When the modified design with open vents is running normally, I saw clock speeds between 2.6 and 2.7 GHz in this test for the most part, which is below the base clock of the Ryzen 7 4800H, as the CPU is running consistently at 95 degrees Celsius in all conditions. However, when taping up the holes, once again, clock speeds noticeably drop on the 2 occasions that I did so, dropping to between 2.50 and 2.55 GHz. This isn't as drastic of a performance drop as I saw with the intense IDA64 stress test I just showed, but combined with the previous 2 tests, it does point to increased CPU frequencies with more airflow into the cooler. Finally, in a realistic workload like Watch Dogs 2, what I experienced was a small increase to CPU package power throughout our testing with the modified base, an increase of about 3 watts with the CPU still running pegged at 95 degrees Celsius. GPU temperatures also decreased by around 3 degrees Celsius, and the performance delta was typically a couple of percent at best. The main thing you'll be getting here are those lower temperatures. So far in my testing, the modified base operating in regular conditions appears to produce a combination of lower CPU and GPU temperatures, as well as improved CPU clock speeds, depending on the exact workload. In the best cases, I saw up to a 600 MHz improvement, but more often the modified design produced around a 100 to 200 MHz clock speed gain when the CPU is running at 95 degrees C. Given that often equates to a 5 to 8% clock improvement, that's a respectable increase for just modifying the bottom panel. Now you might remember earlier that Asus claimed their design delivered the best overall thermal performance. So now it's time to explore exactly why they made that claim and what they are basing that statement off, because as my stress testing has shown, cutting holes in the bottom panel noticeably improves CPU and GPU thermal, so there has to be more to the story. Asus's claims can be broken down into several categories, which I'm going to explore in the rest of this video. The first is that restricting airflow into the bottom of the laptop improves surface temperatures. The second is that it forces airflow over the VRM, preventing VRM throttling. The third is that it lowers the temperatures for other components like the SSD, preventing throttling and extending component lifespans. And the fourth is that adding holes into the bottom panel reduces rigidity. So let's tackle these in order. The surface temperature claim is a pretty straightforward one. Asus originally tested the laptop in a few configurations, the main two being an all-open honeycomb design with full ventilation along the bottom, as well as their final design with closed vents. Their conclusion was that in several hotspots, in particular near the GPU area on the underside of the laptop, surface temperatures were unacceptably high with the open vent solution. However, as you can see from my testing, I'm not using a fully open vent design, but rather one that only has extra intake holes over the CPU and GPU fans. In retaining what is essentially a plastic insulator over the hot GPU heat pipe area, this keeps surface temperatures in check for the most part. In both my testing and Asus's follow-up testing, surface temperatures are largely the same whether we're looking at the stock or modified designs. A few spots are hotter, a few are cooler, but on average it's fairly similar. So you can put this claim to bed. For the most part, increasing airflow in the way I've done it does not impact surface temperatures significantly. Despite Asus initially claiming more airflow leads to a hotter chassis, it seems their final results with the sort of design that I've used here are in line with my results. Next up, we have VRM temperatures and throttling. This is something easy to measure. We placed K-type thermocouples on some of the VRM components corresponding to the hottest areas that we found and reran our standard I-64 stress test that we used previously. In a standard operating environment, so this is 22 degrees Celsius ambient temperatures with the laptop sitting normally on a desk, I did see slightly higher VRM temperatures when increasing airflow to the CPU and GPU cooling fans. Under a sustained workload, I saw peak temperatures increase by a maximum of 4 degrees Celsius and sustained temperatures also increase by 4 degrees Celsius. However, as we're talking about temperatures around 70 degrees Celsius at least, this isn't an enormous difference. The reason why VRM temperatures don't increase by that much is there is still airflow being drawn in through the rear vent over the VRMs and into the cooler. My modified design doesn't remove all airflow restrictions, so the cooler still draws in air through those vents and also through the keyboard. Again, Asus confirmed these results, showing in a standard operating environment under a stress test that VRM temperatures would increase by up to 4 degrees Celsius. It seems Asus were able to locate a hotter hotspot than we found, but again, the difference between the configurations is small. But that's not the entire story for VRM cooling. I also tested the laptop with the base raised to increase airflow into the CPU and GPU cooling fans. This is a standard way you can improve the cooling performance of your laptop, as often the gap between the base of the chassis and the desk is small and restricts airflow. In raising up the base, this could correspond to a number of other use cases like using the laptop on your lap or with an airflow assisted stand. In this configuration, I was able to get the VRM to run much hotter, with sustained temperatures of 95 degrees Celsius and peak temperatures over 100 degrees Celsius in the boost state. Compared to the stock configuration, this was up to a 15 degrees Celsius increase in VRM temperatures. Asus didn't see as significant of an increase, but still saw around a 9 degrees Celsius gain to one component, with another running up to 100 degrees Celsius. What I experienced when the VRM hit 100 degrees is throttling to some extent. In the boost period, I saw intermittent drops in CPU frequency from a sustained 3.0 GHz down to below 500 MHz for about 1 second before returning back to normal. This would cause CPU temperature fluctuations, as you can see in the chart, as well as VRM temperature fluctuations. This behavior appears to be intermittent VRM throttling in the boost state. When the CPU hits its sustained power limit, I didn't see throttling. So at this point, we've found the first issue with opening up airflow to the CPU and GPU coolers, but there's a lot of things to note here. Firstly, Asus were unable to replicate this behavior. Their testing did not see VRM throttling in this configuration, which is a bit of a surprise, but it could be down to sample variance. The VRMs in Asus's testing did run hot, but they didn't see the frequency drops that I did. Secondly, despite VRM throttling, average CPU performance is generally better with the increased airflow design. If we add into the chart what I experienced with the stock base, clock speeds were 100 MHz lower beyond the boost period and up to 300 MHz lower inside the boost period with a more restrictive design. This is because the CPU hits 95 degrees Celsius sooner and sustains 95 degrees Celsius for the entire test, which as we know is the throttling point for AMD's Ryzen 4000 APU. When I cut holes into the bottom of the chassis and raised up the base, I saw up to a 7-degree improvement to CPU temperatures alone, as well as an 8-degree improvement to the GPU. I should point out here that Asus did not see as significant clock speed improvements with the modified base design in this raised configuration as I did, or when also testing on a desk for that matter. However, they also didn't see VRM throttling, so make of that what you will. Again, could be sample variants at play, but they so far have not been able to get it throttling down to as low as 2.3 GHz, for example. But they did see much better thermals with my modified design though, in line with our results. With the VRM running hot, this can impact surface temperatures in this configuration, particularly in the area above the F5 and F6 keys. I saw up to a 10 degrees Celsius increase in this area, although the laptop was still comfortable to touch and other surface temperatures weren't impacted. The results from VRM testing do suggest that increasing airflow to the CPU and GPU coolers does have a negative impact on VRM temperatures. In most conditions though, such as using the laptop on a desk, it's a bit of a non-issue. However, in some specific conditions like raising the laptop up, I was able to get it to throttle in the boost state. This may briefly impact game performance, but overall, and especially when the laptop reaches its sustained level of performance, the increased airflow design still delivers superior CPU performance. Now, looking at this behavior and seeing that VRM temperatures are an issue with increased CPU and GPU airflow, this begs the question as to why Asus didn't put a heatsink or heat pipe over the CPU VRM. Asus even shows in their testing that the VRM can run up to 95 degrees Celsius sustained in a stress test with the stock base. That's pretty hot and not a great sustained temperature, even if in that configuration it doesn't throttle. In my opinion, if the goal was to reduce VRM temperatures, the common sense solution would be to add a heatsink or heat pipe as many other laptop vendors do. Instead, choosing to restrict airflow into the fans, hurting CPU and GPU temperatures in the process, to redirect this air over the VRM is an unusual design decision. Of course, not adding in heat pipes is a cheaper solution, but it's not necessarily better. So I asked Asus why they didn't put a heat pipe or heatsink over the VRM, and this was their answer. We manage temperatures of the VRM and other components by carefully shaping the system airflow. We optimize total system thermals and performance and aim to have a balanced design that ensures the best temperatures, performance, lifetime, stability, rigidity, and reliability of the entire system. A laptop is not like a desktop, it's portable and used in different environments. We optimize for real-world scenarios such as games, content creation, and mixed workloads where the A15 performs as well or better than competing products. There are some interesting claims in there, but I'm not going to dwell on it. You've seen the VRM testing performance. Let's move on. The next claim to assess is that the design lowers temperatures for other components. I'm going to focus on the SSD here as it's the component that Asus has also been focusing on. It is possible that the RAM is also affected, but it's unlikely in my opinion that this component would get hot enough to be of a concern. First up, let's look at SSD temperatures measured using hardware info during our IDA64 stress tests. So while there is a load on the CPU and GPU here, there is no load actually on the SSD. And what I found is that yes, the SSD temperature is hotter with the modified base, up 6 degrees Celsius when using the laptop on a desk, and up 13 degrees when using it raised off the desk for additional airflow, similar to the VRM test that we just went through. Hitting a peak of 57 degrees Celsius with no actual load on the SSD is quite high. However, upon examining the internal design, I spotted something a bit strange. The default position for the SSD is in the left M.2 slot, which sits directly below one of the GPU cooling heat pipes. It's very likely that this heat pipe is transferring a bunch of heat to the SSD during heavy usage. Meanwhile, there's a free M.2 slot over on the right, which is not near any of the CPU or GPU cooling components. If you move the primary drive from the left to the right slot, there is a drastic decrease in SSD temperatures. With the stock base, SSD temperatures drop by 10 degrees Celsius under a CPU and GPU load, while with the modified base, I saw up to a 14 degrees Celsius drop. The modified base still causes the SSD to run hotter, particularly with the base raised, but now temperatures are in line with the full stock SSD and bottom chassis setup. What about load temperatures for the SSD? For this, I fired up Crystal Disk Mark and ran 5 benchmarks back to back and recorded the peak temperature. Most configurations perform similarly, with the exception of the stock base with the SSD in the right slot. However, like we saw earlier, thermals are similar between the SSD in the right slot with an open airflow base and the SSD in its default left position with the default base design. What this tells me is if we had a combined GPU and CPU load in addition to an SSD load, having the SSD in the right slot is better than the left slot for thermals. And while temperatures are hotter with the airflow enhanced design, they shouldn't be any worse than the stock configuration with closed vents and the SSD in the left slot. Granted, if you are planning to fill both M.2 slots, the modified design isn't great due to the problematic location of that M.2 slot underneath the heat pipe. I should also note here there is no storage performance difference between either slot. You'll get the same read and write speeds regardless. Asus did claim that with higher temperatures there was the possibility of SSD throttling, and they showed temperatures exceeding what they claimed was the maximum allowed by the NAND manufacturer. However, in no configuration did I actually see any performance throttling. Now you might be wondering, why is the SSD installed in the left slot by default rather than the right slot? This is another kind of baffling decision given the results I'm seeing. I asked Asus and they didn't directly respond to my question. The final area of interest is the rigidity of the bottom panel. Naturally, cutting more holes into the plastic to increase airflow is going to impact the strength of the panel, and by default the Asus TUF Gaming A15 does have a pretty strong plastic chassis. Unfortunately, I can't properly do any scientific testing on the strength of plastic other than offer my opinion that I believe Asus could mitigate this problem through adjusting the design, improving the thickness of the plastic slightly, or even changing materials. I asked Asus whether they experimented with any other open air vent design that would allow for similar rigidity to the final design, for example thicker plastic or different materials, and their answer was, "We constantly experiment with different materials and designs and continuously improve our products. We optimize total system thermals and performance and aim to have balanced designs that ensure the best temperatures, performance, lifetime durability and reliability of the entire system." I should also note the design is MIL STD 810H certified for drop, shock and impact resistance. I asked whether certifying the laptop for this standard or attempting to lower CPU temperatures and assist with CPU throttling is more important for consumers. And Asus responded by saying, "We don't see this as an either-or question. As with most specs and features of a laptop, it's a balancing act. Different users have different needs and preferences, and we try to ensure that our laptops appeal to a wide audience. That's why we offer silent performance and turbo modes that provide different blends of performance, acoustics, and cooling within the same laptop." The final testing for this video involved cutting out the vents on the right side of the laptop and removing the obstructions to the fin stack that redirect heat into the upper unblocked holes. This was a rather tedious process and I didn't do a great job with it, I'll be honest. The fins aren't that straight and the holes are a bit crap, but it serves the purpose well enough. In my original video, I said that it was baffling that these panels were blocked as it restricts airflow out of the GPU cooler. As it turns out, cutting holes in this area of the laptop made little difference to thermal performance. The system overall performed within the margin of error of our previous modified system in terms of CPU and GPU clock speeds. Asus said they blocked the vents in this way to reduce underside surface temperatures, and this also appears to be true. I saw a small increase to surface temperatures in the region of these vents when they are opened up. Asus saw a larger increase in temperatures than I did, but in general the result is the same. Blocking the vents is marginally beneficial. I was wrong about this one. I assumed that more airflow out of this cooling vent would be better, but as the vent is angled downward and the flow rate out of this vent is pretty low, all that ends up happening is increasing the surface temperature in that area. At this point, this has been a pretty long and thorough investigation of the Asus TUF Gaming A15's cooler, how it's designed, and whether modifying parts of it delivers better performance. We've further explored some of our claims, we've looked at Asus's claims, now it's time to wrap it all up. In my original video, I said the A15 has a terrible cooling design because it runs hot and loud and appears to have been designed without much thought for how air would actually reach the CPU and GPU coolers in an optimal fashion. When combined with the poor display, ultimately I found it hard to recommend the A15, suggesting people either wait for more Ryzen laptop options or look at equivalent Intel laptops like the MSI GL65 for gaming. In further investigating this laptop, my opinion hasn't really changed. I still think this laptop uses a poor cooling solution, and as I've shown throughout this video, making a few small modifications to the design does improve CPU and GPU thermals, and it leads to less CPU throttling. This could potentially have allowed for either better out-of-the-box performance overall, including a lower chance for throttling, or a quieter system that still sits on the edge of thermal thresholds if Asus, ramped down the fans a little bit. Asus, on the other hand, claimed to have designed this cooler with other components in mind, like the VRM, which they didn't put a heatsink on, and the SSD, which they put in the less optimal M.2 slot by default. In addition, Asus are concerned with the longevity and reliability of their products, essentially saying that cooling these other components outweighed running the CPU and GPU cooler when settling on a final design. Ultimately, I'm interested to hear your thoughts after seeing all of this information. Should Asus have prioritized CPU and GPU cooling, or should they have designed it the way that they did? I've no doubt Asus will be watching this video, so leave your thoughts in the comments below. I also want to close out this video just by reiterating that this isn't the only Asus laptop design that features the lack of vents allowing airflow into the CPU and GPU coolers. I did look across a wide range of Asus laptops, and it does appear that this similar sort of design or similar design principles are used for other laptops, including Intel laptops, most oftenly in this sort of mid to entry level price range. But this isn't just a one-off with the TUF Gaming A15. It does seem that Asus's engineers have decided to use this design on multiple occasions, and I think, as we've shown throughout this video, they might want to at least reconsider some of those decisions for upcoming products. Anyway, that is it for this video. The final video that I'm hoping to make on the Asus TUF Gaming A15. Want to put this one behind me. This one has taken an incredibly long amount of time to put together. Doing lots of stress testing and stuff on laptops, cutting holes in it is a very time-consuming process. And as I mentioned earlier, in the process, I've essentially destroyed a $2,000 laptop. So big thanks to our Patreon members who really do make it possible for us to just go out, buy laptops like this for testing, because I'm pretty sure Asus would not have granted us permission to destroy the review unit they sent out for the initial video. Anyway, yeah, you can subscribe for more laptop content and coverage. We're hoping to do a few roundups on the best laptops to buy. There's still a few U-series processors to look at, and well, so I think Intel Tiger Lake's coming out soon as well. So yeah, lots of exciting stuff in the laptop front that we'll be hoping to get to. That's it for this one. Enough of the Asus TUF Gaming A15. I'll catch you in the next one.